In section 4.2, we jump to a topic that seems like it's totally unrelated to what we just learned. Okay? Remember, what is it that we just learned in 4.1? Anti-differentiation and slash, what's the other name for it? Indefinite integrals, right? Indefinite integrals or anti-differentiation. All right, 4.2 is about area. 4.3 is about something called definite integration. And then 4.4 is the magical, wonderful place where we learn about how they combine, okay? All right, before we can get there, first we need to talk about area, okay? So when we talk about area, we're talking about finding the area of something by finding areas of much smaller things and then adding them all up. So we're going to learn some notation that's going to help us with that. And then we will talk about approximating the area of weird shapes, okay? So first thing we need to understand is this sum notation. Have you seen this before? Okay, so sum notation uses a Greek letter sigma. Okay, so that's the big E looking thing here. Okay, on this sigma, we have something below the sigma, we have something above the sigma, and then we have something out in front. Okay, I below the sigma is called the index of summation. So we need to have a letter here telling us what letter represents the letter that's going to change. And then it needs to have some starting value. So in this example given, it's I is the letter we use, and it starts at 1. Sometimes we use J or K there as well. I don't know exactly why, but just by convention, it's usually I, J, or K. And then up top is what we call the upper bound of summation, okay? And sometimes it's going to be a particular value, 5, 10, 20. Right now, this one is in, which means it's some number, okay, some integer. AI is what's out in front of this sigma. This is the term that we are going to sum, and you'll notice it has a subscript I, okay? Since I is the same letter that we see over here, our index of summation, okay, what it means to do a sum, what it means to apply this sigma notation means that we are going to add terms starting with I equals whatever is at the bottom here, our lower bound, and we will increase by one integer increment until we reach in, okay, our upper bound. So in this case, we would start with A1, A2, A3, A4, A5, A6, A7, A8, all the way up to AN, but we don't actually know what in is yet, so we just use the dot, 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 okay? All right. That's the general idea for sigma notation, okay? So let's actually try some, and it'll make a little bit more sense, hopefully, okay? So here, what is our lower bound? 1, so we're starting at 1. What is our upper bound? 6, our index of summation. That's I, okay? And we'll notice that the term out here is just I. That means wherever we see an I, we're going to start with 1, and we're going to add every term incrementing by one integer value. So this is going to be equal to 1 plus 2 plus 3 plus 4 plus 5 plus 6, and stop there, okay? That's what that means. Any questions about how that works? Are you familiar with a factorial using an exclamation point? Okay, a factorial, like 3 factorial, means you start at 1 and you multiply everything up to that point. So 1 times 2 times 3. So that's multiplication, okay? Here we're doing sums, okay? All right, next example. What's our lower bound?
0.
What's our upper bound?
5.
Okay. What we're summing is this whole expression now. We're going to do the same thing though. Wherever we see an I, we're going to plug in starting with 0 all the way up to 5. So our first term will be 0 plus 1. Our second term will be 1 plus 1. Our third term will be 2 plus 1. Our fourth term will be 3 plus 1. Our fifth term will be 4 plus 1. And our last term will be 5 plus 1. Okay. Now we can simplify this. This is the same as 1 plus 2 plus 3 plus 4 plus 5 plus 6. Does that look familiar? Okay, it's the same exact thing as the last one. Why? How is it different?
The starting number.
Okay, so we started at different points and we ended at different points. Okay, and our I don't think there's a name for this, the part that's here, the inside part, the part of the thing that we're summing. Okay, so that is different also.
It's like the I always increase by 1.
Yes, integer by, an integer value by 1. Okay, all right, here's one that's a little bit different. Now we use j as our index of summation. Okay, what is our lower bound? 3. Our upper bound is 7, and we plug in, starting at 3, we plug in for j 3 squared, and we increment by 1. 4 squared, 5 squared, 6 squared, and 7 squared, and we stop there. Okay? Now, those are all pretty straightforward. They're actual values, okay? This is not really what we deal with for the most part. What we're going to be dealing with are more abstract expressions, like this one, okay? And you'll notice there are multiple letters here, okay? We have, what's our index of summation in this problem? K. All right, and we see K in our expression. What's our lower bound? 1. And what's our upper bound? N. You'll notice that N also appears here, but in here does not change, okay? In here is a constant, okay? So there's nothing that we're doing to that N. That N is not changing. The only thing that changes is our index of summation, our K, all right? So the way we would write this is we would take everything that's on the inside here and write it for each term, starting at k equals 1 and moving all the way up through k equals n. So this would be 1 over n times 1 squared plus 1 plus 1 over n times 2 squared plus 1 plus ... 1 over n times n squared plus 1. All right, and you guys understand the ... right? That's everything in between. What do you notice you could do for all of these terms?
You can factor out the 1 over n.
Yeah, you could factor out a 1 over n, okay? And we're going to get some pretty complicated expressions, and we're going to look at some simplification rules that'll help us simplify, make things look a little bit nicer. All right, our last example here is actually even more indicative of what we're going to be dealing with. In the previous examples, our index of summation ended up being a value that was computed within our sum. In some cases, that index of summation acts as the subscript indicating which value of a particular variable you're relating to. So here, our lower bound is 1, our upper bound is n, our index is I. So we're going to start, our first term will be f of x1. Now, does x1 equal 1? No, we don't know what x1 equals, okay? Times delta x plus f of x2, whoops, sorry, that's incorrect. It goes inside the parentheses, x2, delta x plus ... all the way up to f of x in delta x, okay? All right, so now, again, we don't know what x1, x2, x3, xn are, Okay, those are things that would have to be determined some other way. All right, any questions about that? Okay. One important thing to note is that whatever your index of summation is, whether it's I, J, K, whatever, that does not end up in your answer. Okay? Basically what a sum does is it gets rid of that index of summation. Okay? All right, as with most situations in math, there are some formulas and properties of summations that make things a little bit easier for us. All right, and we're going to learn how to apply these for our benefit. All right, the first one is that if we have a sum and it's just a constant value there, okay, that's not changing ever, right? That's the same as saying C times your upper limit. So, for example, you would expand this to be C plus C plus C plus C n times, okay? And if you have C plus C plus C n times, it's just going to be C times n, okay? So, for example, the sum from I equals 1 to 3 of 5, let's say, would be 5 plus 5 plus 5, which is 3 times 5, which is 15. Is that clear? Okay. All right, you'll notice that I starts at 1. If I started at 0, this would not be the same, right? It would be a different sum. You would not get Cn. You would get, what, Cn plus 1, I think. Okay, so that's important. It starts at 1, it ends at n, whatever n is, okay? The next 3 are ones you will need to memorize, and I will add these to your formula list, okay? The sum, and note that all 3 start with I equals 1, and they end at n, okay? You'll need to know the general forms and then how to apply them. So if you know what n is, how to actually do this. So the sum of I, from I equals 1 to n, is always going to give you n times n plus 1 over 2. I want you to prove it to yourself. Do this sum. The sum I equals 1, let's do to 3, of I. Do it right now. Do it right now on your paper, okay? Do it the long way, and then you can also try it the shortened way. Okay, did you get 6? Okay, so if we do it the long way, writing out 1 plus 2 plus 3, we get 6. And if we get the plugging in version, 3 times 3 plus 1 over 2 will give us 12 over 2, which is also equal to 6. What is the advantage of this second way of doing things?
If that goes longer, like 1 plus something plus 1 plus 2 plus 3, all the way to 100, you can do that.
Exactly. Perfect. Yes. So if n was 100 or 1,000 or 10,000 or 1,000,000, okay, obviously you don't want to be sitting there writing down every term, okay? So this nice formula lets you simplify it, okay? All right, we can do similar formulas for I squared and I cubed. Once again, you need to memorize those, okay? And these have properties just similar to limits and derivatives, okay? If we have the sum from I equals 1 to n of some constant times a term that involves I, we can factor that constant out, okay? So if we want to make things simpler, okay, we can factor it out just like that, okay? And if we have the sum of two things added together, that's AI plus or minus BI, okay, from I equals 1 to n. that's the same as two separate sums. The sum ai equals 1 to n of a1. I'm sorry, I equals 1 of ai plus the sum from I equals 1 to n of bi. Okay, so we can separate them out just like a lot of the other rules we've seen. Okay, we're going to apply these to evaluate this sum for several values. And you'll see here we start with 10. 10's not too bad. We could do that by hand. But then we have 100, 1,000, and 10,000, which we definitely do not want to do by hand. Okay. First thing we need to recognize in this sum is that we've got a constant. What is our constant? What is this being multiplied by? That's it, 1 over n squared, okay? 1 over n squared behaves like a constant. Even though we see n squared even though we see n up here and n is a letter, not a number, it behaves like a constant because it's not I. All right, so we could factor out a 1 over n squared. That leaves us with the sum from I equals 1 to n of I plus 1, okay? Now we can use the rule we just looked at. Again, 1 over n squared is our constant. And this is the same as the sum from I equals 1 to n of I. Sorry, that's an I. Plus sum from I equals 1 to n of 1. So we separate it into two separate sums. And now we look back and see what is our formula for this one. For I equals 1 to n of I, the sum is n times n plus 1 over 2. How do we know that? There we go. Our formula is here. Okay. So the sum from I equals 1 to n of I is n times n plus 1 over 2. And then the sum from I equals 1 to n of 1 will just be 1 times n or n. Okay, again, going back to this one, our very first rule, all right, 1 is our constant, so it's 1 times Cn, so C is 1, so just 1 times n. All right, the final thing we want to do is simplify here, and we'll take a look. Let's put it into a single fraction, okay? So first, 1 over n squared, and put the inside here into a single fraction. That's going to give us n squared plus n plus 2n over 2, okay? Which is 1 over n squared plus 3n over 2, which is n. We can factor out an n from both, right, and cancel it. So we end up with n plus 3 over 2n. Okay. Now, the second part of the question asked us to evaluate it for particular values, 10, 100,000, and 10,000.
Is that, that should be like n times n plus 3 over 2?
No.
Or
there was a...
There has
Okay. So, when n equals 10, we plug in 10 plus 3 over 20. We get 13 over 20, right? In decimal form, that's 0.65000. Okay. For n equals 100, it's 100 plus 3 over 200. So 103 over 200. 0.51500. For n equals 1,000, it's 1,000 plus 3 over 2,000. So 1,003 over 2,000, which is 0.50150. When n equals 10,000, now we have 10,000 plus 3 divided by 20,000, which is 10,003 divided by 20,000, which is 0.50015. What do you notice happening as we increase n?
Closer to 0.5.
Okay, it's getting closer and closer. You'll notice it's this 3 that's changing things, right? It's the only reason it will never equal exactly 0.5 is because that little bit of 3, okay? Otherwise, you would have exactly 1/2 in each term, right? As n gets bigger, that 3 matters less and less, right? It impacts it less and less. The difference between 13 and 20 and 103 and 200 is significant, right? Okay, good. Any questions? All right, so your question probably is, why does this matter? And again, we're going to talk about area here, talking about indefinite integrals in the next session, and then we'll talk about how to tie them all together. All right, here's the deal. From geometry, all right, in order to determine the area of a shape, either that shape needs to be a regular polygon, meaning it's got nice straight edges and some sort of geometry that can be broken down into either squares or rectangles or triangles, okay? Or we have to approximate the area using some trickery, okay? And this is how the area of a circle came to be, okay? We know that the area of a rectangle is base times height, okay? From there, we can determine the areas of other things. But the circle is one of our weird things to look at, right? You'll notice in this first image here, the orange one, that we've got 2 polygons, 2 pentagons, okay, more specifically, one inside the circle and one outside the circle. What can you say about the area of the pentagon inside the circle?
Less than the circle.
Okay, the area inside is definitely less. And what about the pentagon that is outside? Okay, it's larger. It's definitely bigger. So we know that the area of the circle is less than the area of the big pentagon and greater than the area of the little pentagon. Okay, so we know that for sure. So what can we do to get a better and better approximation? Okay, in this case, we've got 5 points. We can get a better approximation if we increase the number of points on our polygon. So you'll notice here that the area between the 2 pentagons is greater than the area between the 2 hexagons, right? That purple area between is smaller. And if we increase it one more time to an octagon, what happens? It's even smaller, okay? So if we can take the area to the limit on either direction, take the area of the bigger one, make it smaller, take the area of the smaller one, make it bigger, we can get the exact area of a circle, and that's exactly what was done. Okay, we'll pause there, come back to it tomorrow.